All right, carboxylic acids. Carboxylic acids can contain the carboxy group. So this group right here is the carboxy group. May or may not remember that from 51A. And we have a couple shorthand ways to write carboxylic acids. I want you to be familiar with both of them. We can use CO2H and we can use COOH. I normally choose this way to draw it. I think if you write it as COOH, there's a tendency for students to write it like it's a peroxide and not a carboxylic acid. So those are the two shorthand ways of writing it. Let's talk about structure and physical properties. We definitely know that carboxylic acids are resonance stabilized. So let's draw some resonance structures. We're going all the way back here to 51A. So we can certainly move electrons up onto oxygen and break that pi bond. And really, we can do that with all of the carbonyl compounds, and we will be doing that with all of the carbonyl compounds. That leaves us with carbon without an octet. It's a small resonance contributor, but it is a resonance contributor. And then the other thing, we can have the electrons on oxygen come in and kick in, and we can put a double bond between that carbon and oxygen. That leaves us with a positive charge on oxygen and a lone pair. So definitely resonance stabilized. Carboxylic acids are resonance stabilized. And if we draw the hybrid, again, all the way back in 51A, pretty much everything you've learned all year comes back in 51C. So. All right, so we draw all the bonds that aren't changing. When I draw hybrids, I usually leave lone pairs off. And if I ask you to draw a hybrid, you can leave the lone pairs off. But you can see that we're going to have a partial bond here. Any bonds that change are dotted. And we also have some partial charges. If you look on the carbon of the carbonyl, it has a positive charge in the middle resonance structure, so it would be partial positive here. The oxygen has a partial positive charge also, because we see a positive charge on the third resonance structure. And then certainly we have a partial negative charge on the carbonyl oxygen. All right, so that's our hybrid. And so what we say is that this has double bond character. Here's our double bond here. Here's our double bond here. So we have double bond character. And so what does that mean? That means that bond is shorter than a normal single bond, but longer than a normal double bond. So this bond is shorter than a typical carbon-oxygen double bond, or shorter than a typical carbon-oxygen single bond. And then if we look at physical properties, just comparing, we'll compare a carboxylic acid with an alcohol, with a ketone, and with an alkene, just to see what we have here. Boiling point of the carboxylic acid is going to be the highest. 117.9. You do not need to memorize these numbers, but I do want you to know the trends here. 82.3 degrees for an alcohol. 56.5 degrees for the ketone, and minus 6.9 for the alkene. Percent solubility in water infinite for all three, for the first three compounds. infinite solubility, 0% solubility for the alkene. So one of the questions is, why do the carboxylic acids have such high boiling points relative to many other organic compounds? And the reason is they form very strong hydrogen bonded dimers. So let's draw what one of those looks like. They form strong hydrogen bonded dimers. So we'll draw one carboxylic acid here. So there's one, and the oxygen of the carbonyl is going to want to do a hydrogen bond with the hydrogen of the other carboxylic acid. There's one hydrogen bond, here's the other hydrogen bond. Okay, so there's a hydrogen bond dimer. That's going to dramatically increase the boiling point. And then when we extend the length of the carbon chain, as you would expect, the boiling points are going to go up. So adding one carbon, we have 141. One more carbon, 163. So as we increase molecular weight, we're going to increase boiling point. 186 here. And 205. So predictable increase in boiling point as we increase the length of the carbon chain. And then solubility, as we would expect, is going to go down. So infinite here, and then we start getting to a point where we have too many carbons and not enough oxygen. So this would be 3 grams per 100 mils of water. Again, numbers are not, you don't memorize these numbers, we just want to know trends. And then we go down to 1 gram in 100 mils of water. All right, so definitely a trend that we would expect, that you would have predicted back in 51A. Why do we have this trend? If we increase boiling point, why do we have increased boiling point? Because we have increased molecular weight and increasing van der Waals forces. And solubility goes down, on the other hand, as we increase molecular weights. We decrease solubility because the nonpolar hydrophobic portion of the molecule is getting larger. So as the nonpolar hydrophobic portion gets larger, when this gets larger, the solubility decreases. All right. Questions so far on structure and physical properties. So no great new news here. Nomenclature, we have a handout and we have a podcast. The podcast is not posted. It will be under the practice link, and I'll let you know when we're ready to do that. You don't have to do nomenclature of carboxylic acids yet. So what I like to do is do all of the carbonyl nomenclature together, and that will all be on the podcast, and I'll let you know when that's going to be posted online. It's already done. I just need to post it, and you guys will be set. All right, so now we're to the portion of the chapter, Acidity of Carboxylic Acids. If you had me for 51A, my notes are almost identical to this, if you go back and take a look at the notes for 51A. So it really is a 100% review. So of course, when we treat a carboxylic acid with a base, we're going to deprotonate the acidic hydrogen that's bonded to oxygen. that gives you a carboxylate ion. And whatever the base you use, we get the conjugate acid, BH. And it turns out that the carbonyl greatly enhances the acidity of carboxylic acids. So if we compare here, we have pKa about 5. It's actually 4.8, but pKa about 5. And for water and alcohols, these would be pKa of about 15. So something pretty close to 15 here. So if you had my class for 51A and 51B, those 8 pKa's that you had to know rounded to the nearest 5, that's also going to come in this quarter. Also, we're going to add a few things, though, to that, just a few carbonyl compounds. So I'll let you know when that's going to happen. So why are carboxylic acids more acidic? One of the first things we like to do when we're comparing acid strength is to look at the conjugate base. That's usually a very helpful way to go. So let's look at the conjugate bases and see if we can explain. So we'll just pick methanol. Methanol would be very similar to water, but let's pick methanol. Let's look at the conjugate base of methoxide ion. And let's compare that with the conjugate base of acetic acid. Oops, I don't want that protonated. All right, so we know that the conjugate base of acetic acid, we know that that is resonance stabilized. So we can push electrons, we can share those electrons between 2 oxygens equally. And that's because we get 2 equivalent energy resonance structures. And when you have 2 equivalent energy resonance structure, that typically makes the compound very stable. So we have 2 equivalent energy resonance structures. All right, so what do we have? Do we have any special stabilization? So definitely the conjugate base of acetic acid, carboxylate, is resonance stabilized. Do we have resonance stabilization for methoxide ion? Anybody? So what we can say is that, yeah, there's no resonance structures. Electrons are localized. Oh boy. Electrons localized on oxygen. And certainly over here, the electrons are delocalized onto 2 oxygens. It's always better to have delocalized electrons. Always better to have delocalized electrons. So when you delocalize onto 2 oxygen, it's also really powerful, as we're going to see coming up, that delocalizing electrons onto oxygen is very good when we can delocalize onto oxygen. And so what we can say here is that the conjugate base is resonance stabilized. And since the conjugate base is resonance stabilized, that means it's going to be more stable. So we have a more stable conjugate base. If we have a more stable conjugate base, what does that mean about the conjugate acid for that? It's going to be more acidic, right? So the acid's more acidic. So anything that we can do to stabilize the conjugate base makes the acid more acidic. Super strong acids have very, very weak conjugate bases. Okay, so just something to keep in mind. All right, so that's reason number one. And reason number two is that we actually have an inductive effect going on here that's probably not as obvious to you. So let's draw out our carboxylic acid. This is just another way to think about it. And we know that the oxygen is more electronegative than the carbon, so we already have some good polarization of this bond here. Partial positive here, partial negative. And so, what we end up having here is electron density. The carbonyl is actually an electron withdrawing group, just like we talked about in chapter 18. So it's pulling electron density away. So the carbonyl group inductively draws electrons away. So it is an electron withdrawing group, which I abbreviate EWG. All right, so what does that do for our conjugate base? Here's our conjugate base, carboxylate ion. And so what we have here is we have pulling electron density away here. Is that going to make that more stable or less stable? More stable. So the inductive effect of the carbonyl makes oxygen. It's pulling some electron density away from oxygen, makes oxygen less negative and therefore more stable. So more stable conjugate base means the acid is going to be more acidic. And it turns out that if we have substituents, so that would be just plain acetic acid, but if we have substituents attached to nearby the carboxylic acid, that's also going to affect acidity. So anything that stabilizes the negatively charged conjugate base is going to make the corresponding acid more acidic. So if we look here and we compare acetic acid with carboxylic acid with a chlorine bonded, and what we're going to, when we do the nomenclature, you'll see that this is the alpha position. There's chlorine in the alpha position. And so what happens to the pKa there when we have a chlorine in the alpha position? This is 4.8, and this pKa moves up to, or moves down to 2.9. So it becomes more acidic when we have a chlorine adjacent to the carboxylic acid. And how we can explain this is how we usually explain things when we're comparing acidity. We look at the conjugate base. All right, so this chlorine is inductively electron withdrawing. And so what it's going to do is going to pull on that electron density. It's going to pull electron density away from oxygen, just like this. So the carboxylate is stabilized by the inductive effect of the chlorine substituent. And that's just simply because it's making oxygen less negative. A less negative oxygen is going to be more stable. So therefore, the conjugate base is more stable. So here we have not only the inductive effect of the carbonyl, we also have the inductive effect of the chlorine adding together. Therefore, the conjugate base is more stable, and therefore the acid is more acidic. And definitely this next slide, this is the inductive effect of other substituents on the next page. And definitely this is straight off of my 51A notes. So let's take a look at this. And this is just kind of comparing different groups that are in the, again, the alpha position. So basically what we have here, let's look at the conjugate base, what this is going to do for us. We'll just repeat what we did on the previous page. If we have an electron withdrawing group here, EWG, it's going to pull electron density away and stabilize the conjugate base. And if depending on how good that electron withdrawing group is, it's going to do a lot of stabilization. It's going to do a little. It's going to affect the acidity. And so if you look here, well, we're comparing X, 4.76. And so that's sort of our standard there. That's acetic acid with no substituents. And then if we substitute iodine here, we say iodine, bromine, and this gives you electronegativity. So as the electronegativity is getting larger, the pKa is dropping. Okay, so fluoride, more electronegative than chloride. And so it's going to have a more powerful electron withdrawing effect. It's going to pull electron density away. It's going to make oxygen even less negative. So the more electronegative the electron withdrawing group, the more acidic the compound. So that makes good sense. These guys, we can't really give them electronegativity because electronegativity is for a single atom. But these are electron withdrawing groups. Okay? So they're electron withdrawing groups. And you can see 3.83, so hydroxide, not super good. It's not even as good as iodine. And we're used to thinking of hydroxide as an electron donating group in chapter 18, right? It can be both. When it's in the alpha position, it can't do anything with resonance. So it's just simply an electron withdrawing group. Cyanide, also an electron withdrawing group. It's about the same as, well, it's about a little bit better than fluorine, right? So it's kind of nice to have a measure of that. Nitro is the most powerful of all, 1.68. So you put a nitro group in this position here. Well, there should be a carbon there too. You put a nitro group in this position, and it's going to be even a stronger electron withdrawing effect. Methyl is actually the opposite. That's electron donating. And so this would be for this one here. This is an electron donating group. And let's go ahead. I should fix this. I'll let you fix this. We forgot, we dropped our carbon here. So let's fix that first, and then we'll do methyl. So CH2, and this is EWG. So I want to fix that there. That's better, right? So we're going all the way here. For the methyl, that's the opposite. That's an electron donating group. It's not a very powerful electron donating group, but it's slightly electron donating. So that's actually pushing electrons in the opposite direction. It's very weak, but you can kind of see pushing electrons in that direction. And so it's actually making it less acidic than acetic acid. Not a very powerful effect, but it is slightly electron donating. All right, so to summarize this, let's label these guys here. Here we have increasing electronegativity. Increasing acidity. And this probably makes a lot more sense to you now than it did even back in 51A, because we've had so much more chemistry. These guys are also electron withdrawing groups. And want to make a note of this, nitro is the most powerful, strongest. So when I say we want to make a note of it, that usually means I'm probably going to ask you a test question about it. So just to give you that, right? You want to make a note of that. See, now that might be cut out. I don't know how they edit this, but that might be cut out, what I just said. Okay, so that's the strongest electron withdrawing group. And then this one actually has a higher pKa because it's an electron donating group. It's not by much, I agree, but it's got a higher pKa. It does give you the idea here. Higher pKa than acetic acid, which is the unsubstituted version. And that's because CH3 is slightly electron donating. When we have electron density flowing towards oxygen, it's going to make it more negative. This makes oxygen more negative. More negative is less stable. All right, so therefore the conjugate base is stronger. And therefore the acid is weaker. And we're going to do this again when we talk about amines. We're going to spend a whole lecture talking about acidity and basicity of amines. So this is same sort of thought process there. And inductive effect decreases as the electron withdrawing group gets further away. So we start off here. This is 2.97, and we jump up to 4.01, and then we jump up to 4.59, and then we jump up to 4.71. So we're almost to 4.76, right? We're getting there. And so as this group gets further away, its effect falls off pretty rapidly. Okay, so a big difference there. All right, let's do a couple more acid-base examples. How about this one? Which one do you think is more acidic? First one or the second one? First one? Not a profound difference, but the first one is definitely more acidic, 4.2. And this is pKa 4.8. And so how do we explain this? We're going to do the same thing we did previously. Look at the conjugate base. It turns out that the phenyl group, the benzene ring, is slightly electron withdrawing. So if we compare benzoate ion with carboxylate acetate ion, this is an sp2 carbon, right? sp2 carbon. More electronegative than an sp3. So it actually, an sp2 carbon is going to be more electronegative. It's going to pull electron density away. It's behaving just like an electron withdrawing group. So inductive effect. Stabilizes the conjugate base. And anything we do to stabilize the conjugate base is going to make the acid more acidic. Therefore, the acid is more acidic. All right, so might have some carboxylic acid acidity trends on midterm 1. Pretty darn likely. That's sort of a must, okay? All right, let's do one more example. Which do you think is the most acidic? First one, second one, third one? I heard it's the first one out there. All right, pKa 2.2, 3.4, and 4.2. So the nitro group makes a big difference. It makes the biggest difference when it's the closest to the carboxylic acid. Inductive group falls away rapidly as you get increasing distance. So we're going to look at the conjugate base again. Here's our carboxylate. And we'll put the nitro group in the ortho position. And you can see that this nitro group, very powerful electron withdrawing group, more powerful than fluorine. It's going to pull electron density away. Strong inductive effect. The closer, the better. Strong inductive effect stabilizes the conjugate base. How does it do that? It makes it less negative, the oxygen less negative. Therefore, the acid is more acidic. Over here, with this one here, the nitro group is further away. It's as simple as that. Electron withdrawing group farther away. Therefore, inductive effect is not as strong. All right, so this is going all the way back to chapter 2 on our acid-base chapter. So let's look at some common bases used to deprotonate carboxylic acids. You may run across these in the lab. Did you do an acid-base extraction? Was that last quarter or is that this quarter? Last quarter. So you encountered this in lab last quarter. An acid can be deprotonated by a base that has a conjugate acid with a higher pKa. Since pKa's of many carboxylic acids are about 5, bases that have conjugate acids with pKa values higher than 5 are strong enough to deprotonate them. So that's what you want to look for. And so some typical bases, these are some typical bases, let's finish that sentence, that are used to deprotonate a carboxylic acid. All right, and notice the conjugate acids of those bases are all greater than 5. And that's what we want to look for. Notice pKa of the conjugate acid for all of these bases is greater than 5. Could we use chloride ion to deprotonate a carboxylic acid? No, because hydrochloric acid has a pKa of -7. You have to be greater than 5, and usually significantly greater than 5. So let's show you why that works. Let's use ammonia, the second one on this page. Let's use ammonia. Write out the acid-base equilibrium. So we have that, we have ammonia. Let's do arrow pushing. Let's finish writing out the acid-base equilibrium, and then we'll note the direction of the equilibrium. So here's our carboxylate. Our conjugate acid is ammonium ion. So to figure out the direction of equilibrium, we look for conjugate acid-base pairs. So here's our conjugate acid-base pair. And the one that has the extra proton, that's our acid. And then here's our other conjugate acid-base pair. And this one has the extra proton, so this is our acid. We should have one acid on each side of the equation. And then we look up the pKa's for those. pKa, about 5. And pKa. If you had my class last quarter, you will recognize these as one of the ones you needed to know rounded to the nearest 10. pKa about 10 for ammonium ion. All right, so that means the equilibrium very highly favored to the right. And one of the things, the other things that I do is kind of do an estimation of how much we have of each reactant and product. We take the difference in pKa, so that would be 5. And so at equilibrium, we have about 1 reactant for every 10 to the 4th of products. So that means that that's a really good base to choose to deprotonate. If we tried to use chloride ion to do the same thing, the equilibrium would be in the opposite direction. Okay, so those are some common bases that we're going to use. And in the last minute, we'll talk about just some review reactions for how we talked about preparing carboxylic acids. H2CO3, actually you can't put that in a bottle. We get that from mixing CrO3 and H2SO4. There's those reagents again. Or some people like dichromate. I don't know. I don't like this one as much. Cr2O7 and H2SO4. Can we use PCC for this? No, no PCC. Why? Does PCC, what does PCC give you with a primary alcohol? Aldehyde, not a carboxylic acid. So we can start from a primary alcohol. We can also start from an aldehyde. We will get a carboxylic acid. We can also do ozonolysis of alkenes with a oxidative workup. These are the things you forget over time, reagents. But if you understand the chemistry, then that should be the thing that you don't forget over time. If it's an alkyne, we don't have an oxidative workup, we just have a water workup. Again, something that you're probably not going to remember. And that's why you want to be doing those synthesis problems at the end of each chapter, because it will remind you of these reagents. It's time to stop now. We'll continue this on Wednesday.